work very briefly. I had a few people send stuff to me. I think we'll do, let's see. Who wants to share? I think Dan Yee sent me some, so we'll take a look at Dan Yee's. Dan, where'd you send yours? Am I blind? Was it in the workshop channel?
Discord DMs.
Discord DMs. Oh, that's right. It was up because we were chatting earlier. Yeah. Let me download this homework1.c. This is going to be open in I'm going to open it in Notepad and then copy it in.
Notepad. That's what I used to do in 333.
Bruh, I did Notepad++ for a while, and then I'm like, this thing does not have code, fucking whatever.
I never installed
Alright.
IDE in 333 because I was just like, I mean, Notepad works, and Phipps was like, it is what it is.
Alright, let's take a look at what we have here. Question 1.2. What was question 1.1?
Not a coding question.
Oh yeah, that's right. You had submitted a doc as well, so let's take a look at this. I was gonna do my own homework, but then I didn't because I was at the mall today. Okay, hang on. What? I just X'd out of Microsoft Office. Kill me now. Hang on. 1 second. I had it opened, and then I was like, oh, it gave me some big pop-up that was annoying me. No, I don't. Okay. Thank you, Microsoft Office. Alright, for the first one, 1.1, why does the following code print out, and why isn't it 5? I'm told here that it prints out 3, and yes, this is because of short-circuit evaluation for a Boolean expression. Let's see, and C, any number that isn't 0 is considered a Boolean value of true. Exactly. The Boolean expression inside the code evaluates the first operand as false. Yes, 0 evaluates as false. And because of its logical and, it does not need to evaluate any farther. Exactly. Yeah, that's exactly right. Okay, so then 1.2 is a coding question with De Morgan's laws. So effectively, this is one way of doing it. I think someone else used a for loop here, but I didn't teach for loops yet, so that's fine if you used one. It's fine if you didn't use one. This is actually a good example of where you would want to use a for loop if we had been doing for loops already. So let's briefly look over this. I'm actually really happy that we don't have that many people today. It's very nice and it's comfy. So the De Morgan's laws, De Morgan 1, A, and B. So effectively, you're supposed to have it always evaluate to the same thing. So this evaluates to the same thing. Good. This evaluates to the same thing, good. This evaluates to the same thing, good. And this evaluates to the same thing, good, right. So these two expressions should evaluate for any set of true or false inputs, which, yeah, you have there. Right, okay, good. So let's take a look. Is this still, where are we? Third bit. Question 2.1, yeah, okay, so we're on 2.1 now. Print the third bit. So the way that you do it is you shift first and then you AND with the mask. This is correct. You can do the mask first like Max did, or you can mask first, shift second, or you can shift first, mask second with the AND. Yeah, so this is good. Again, you could have this be 55 and it's the exact same thing. Yep, okay. 2.1, negate a number with 2's complement using bitwise, not, and a +1. So this is right. You literally just flip all of the bits of the number, and then you add 1, and that results in the negation. Enter a number. The negated number is 0. Are you scanning for this? So if I put something in here, will it tell me what the negative of it is? So if I put in 55 on the first line, negative 55 negates to 55, good. And if I put in 55, it should negate to 55, yeah. So to negate a number with 2's complement, you flip all of the bits and then you add 1. That's just 2's complement. So very good, that works. Question 3.1, a 2-line program that works differently when you swap out ++I with I++. So this is a perfect example right here where I++ and ++I evaluate to different things. I equals 0. In this case, the printf you're passing, it's evaluating first. So it's reading what I is, and then doing it after the line executes. So this is equivalent to printf I and then doing I plus equals 1 on the next line, whereas the second one adds it first and then reads it beforehand. So this would then be equivalent to putting the I plus 1, I plus equals 1 here instead. Yeah, so this is correct. Yeah, you can literally just have a program that prints and reads it on printf. So yes, this is a 2-line program. Very good. All right, next up, write a program to compute the date of Easter Sunday using the provided algorithm. Okay, very good. So you declare all your variables. I actually didn't show that you could declare multiple variables like this yesterday, which may have been a good thing to show. So this is literally just equivalent to saying int A, I'll do capitals, then int B, you can just put commas between variables of the same type if you want to declare multiple variables on one line like this. So this is good. So did you, it doesn't look like you used the same naming convention that they did. You just went down the alpha. Oh, did you use the same naming convention? Oh, you just had year instead of Y. Okay.
I changed that.
Okay.
That's it.
Yeah. Good. Also for question 2.1, I++ is post increment, and yeah, increments after the line is executed, ++ I is pre-increment, and increments before execution. That's correct. So good work there. And then this algorithm works, I take it. In the year of,
I don't know why it says 194 where it got it from.
Let's see. So by default, if you don't this is actually an interesting thing in C. If you don't initialize a variable in C, it does not default initialize to 0. It has random junk in it that was in round. It does not like overwrite that or anything, which is different from other languages, which sometimes will initialize their variables to 0. C does not initialize your variables to 0. It just takes random junk. So you're scanfing year, but there's nothing being read here. So if we add another thing here, so let's say what's the demo that was in the homework?
One, which was like 8. I forgot what day it was. You know, I probably have homework.
All right. In the year 2001, Easter Sunday falls on the day 15 of month 4. I believe, yeah, that's April 15th. Of the Gregorian calendar. Yes, very good. So this is a good, I believe that this is the correct algorithm provided. So some other people submitted homework as well. I know Max submitted homework, and Edgar also submitted homework. So we can take a look at, let's see. Did anyone else submit homework? I don't know if anyone else submitted homework. Let's see. I will take a look at, Max didn't submit all of it, so we'll just take a look at Edgar's real quick. I'm assuming most of this is, I took a brief look at Edgar's, and most of it looked like it was correct. So we just want to make sure that, let's see, all right, so problem 1A, let's see, this was the, yeah, okay. So this is because 0 evaluates to false and it short circuits, right? Yes. And the code prints 3 because, yes, the AND operator evaluates to false due to short circuiting, right? And does not get assigned value of 5. Good. Hang on. How is my... That's kind of annoying that I can't, like, scroll over on tier, but that, whatever. All right, 1B, let's see, De Morgan's laws, you used a for loop here and a case statement to do the assignments. Let's see, so when A is false and B is false, then you have the not values printed out here. This is what we're interested in, is comparing this guy and this guy, true, 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 and false, false. Very good. Okay. Next up is the negation question, or is it the shift question? Print a bit in position 3 of the number 55. Bit shift 3, I'm assuming there's a computation at the end here. Yes, there is. number, bit shift number, and then number shifted over by the bit shift minus 1. Okay, that's equivalent to shifting it over by 2 effectively. Then you do the mask with 1. Yeah, correct. Good. Negate number with 2's complement, number negated plus 1. Good. Exactly. And finally, the algorithm here, and I'm assuming this is correct. Yeah, in 2001, Easter falls on 4/15. All right, beautiful. I'd go over Max's homework, but Max isn't here. Glad to see some of you are taking this seriously and doing the homework. All right, so next up, we are going to be discussing so that was actually pretty good. We were able to get the homework out of the way within just 15 minutes. So the next thing that we're going to be talking about today is if statements and everything else. Let me pull up my sheet that I have for today. Hang on, where did I drop the syllabus? It's probably in my, let's see, should be in my drive. If I can find where my drive is. Oh man, they signed me out of Google. What? Able to do... Hang on, gotta make sure I put this in there. Are they gonna do a check on me? No. Okay. Pretty sure this is the syllabus. Okay. So we are looking right now at day 2. All right, so today we are going to be going over conditional control flow, which is everyone's favorite if statements, switch statements, and we'll also be covering the ternary operator really quickly, which is just a fancy way of doing an inline if statement. Love my ternary operator, use it all the time. Then we're going to be going over fixed arrays, which are, we're not covering pointers, we're covering pointers tomorrow, that's tomorrow. Today we're just going over fixed size arrays. Then we're going to be covering loops, and finally basic functions. Okay, so first thing is first, let us get started with if statements, which are a big, all right, let's X out of here. We're going to go to I just open up like an entirely new cloudbolt.org instance that doesn't save all of the code. Apparently not. I'm just going to yeet everything. Give me a second. Very nice. Now let us begin. Okay. So first things first, for if statements, the motivation behind if statements and conditionals is the idea that effectively when we're writing a program, we need to know whether or not we should execute code based on some condition. This is very common. In fact, most human thought processes as well are determined by logic-based conditionals, right? So you should go to the grocery store if there is nothing in your freezer. We need some way of being able to represent that programmatically, right? So that and every single other reasoning process you could possibly imagine based on some condition. Very important in programming. In fact, there's entire programming paradigms, logic programming, where everything is just logic, and you're doing, the entire thing is basically what if statements evaluate to behind the scenes. But for our purposes in C, if statements are pretty straightforward. They take the form of if, and then parentheses, and then curly braces, okay? So the curly braces contain statements. Normally the statements are indented, and every statement within this big block inside of the if is executed in the event that whatever is inside of these parentheses evaluates to true, or in our case, true being anything that's not 0. So basically, if this is 0, then whatever is in here does not happen. If it's anything else, it does happen. So I'll just do a quick little printf demo here, hashtag include tdio, so I can get printf. Hello. Okay. So basically, this is going to print hello if whatever is inside of these parentheses evaluates to anything that's not 0. And this could also be, if we have bool in here, this could be true or false. So why don't I also include stdbool.h so we can demonstrate this. So in the event that this is non-zero, if this is 1, we can see that we're printing out hello right here because whatever is inside of these parentheses evaluates to 1. Same thing with 2. This can be any other number. As long as it's not 0, this code executes, right? 7, some really long number that's not 0, right? All of this evaluates to true. And 0 is the only thing that evaluates to false. When we include stdbool.h, true and false both evaluate to 1 or 0. So if I have if true here, this evaluates by default. If I do if false, this obviously doesn't evaluate. So this isn't very interesting, though. This isn't, why should we care about this? Like, this is just a constant, and we really don't care whether or not we have a constant. What's more interesting is if we're determining to execute stuff based on user input. So let's take a look at a real example of something you might do. So let's have let's call it password. So we're going to have a secret password and only execute code if the user inputs a number that we want them to input. So I'm going to have the password be some long number, and we're going to then scan F for that number. So %D, and we're going to have them get that number. So we're going to require the password. And you know what, while I'm at it, I'll have a printf that says, no, you know what, that doesn't even matter because we're not actually outputting anything here. So we'll get the password, and then we're going to check if the password matches what we have put in here. So if password, and then we'll put the password in here. We'll have the password be 1234. How does this look? So now if the user enters a password that's wrong, it's not going to say hello. We'll have it say you have entered the secret password. You have entered the password correctly. So we only get this message to print out in the event that the user puts in the correct password here in our input. So let's try putting in the correct password here, 1234, and they've entered the correct password, and look at that, we have entered the password correctly. Right, so this is pretty straightforward. We're using the equality relation operator here. So this returns the number 1 in the event that this holds. If password is 1234, then we execute this code effectively. So this is a very basic if statement example. So one thing that's interesting in C that I should actually be looking at what the hell is going on in the background? That was sent, what, 3 minutes ago? What was going on in the background? I missed it. Was something going on in the background? It was probably me, like, whacking my microphone by accident, most likely. I seem to do that quite often. Okay, so this is our basic if statement example. Let's bulk things up and add an else on here. So an if-else statement is a special variant of an if statement where whatever's in this second block right here between these parentheses, between these curly brackets, is executed in the event that this fails. So if this condition is false, then we're going to execute whatever's in the second block. But if it's true, we're executing whatever's in the first block. So a good case here for our if-else statement would be to then tell the user that they did not enter the correct passcode. So you did not enter the right code. So in the event that we enter the wrong code, so SDA, sure, why not? SDA isn't even a number, so you did not enter the right code. So every single time we get that you did not enter the right code, unless you entered the password correctly and you enter a 1234. So let's see, 1235 did not enter the right code, 1234, and you have entered the password correctly. So this is a very, very simple if statement here where we're inputting some password and then checking if the password matches and then executing some arbitrary code, in this case printing out whether or not they actually entered the password correctly. So that's a very basic little if statement right there. If-else statement right here. So we can bulk this up further by essentially having if-else chains. So if-else chains they give us the ability to evaluate multiple conditions and see if multiple conditions, so if the first condition fails, then check another condition, then check another condition, and evaluate code based on various things. So we can have password 1, and here we'll say you put in password 1, and then we'll do else if. Let's see. So we'll have a second password. The second password will be, let's have it be 3333, and we'll have this be password 2. So printf, you entered password 2. And then else if chains, we can just chain these basically forever. For those of you who know Java, this is probably hilarious because you would never actually do something like this of 4444, 5555. I think we'll just go up to 5555. Let's see. 2. This will be 3. This will be 4. And finally, we'll end with an else statement that tells them that they did not enter a correct password. You failed at life. There you go. Okay. So now we're effectively evaluating. Oh, they're mad at me. What? Password 1, password. Oh, I don't know why I called this password 1. I can get rid of this. Well, you know what? If they can't guess one of our passwords, they fail. Okay. So effectively here we have an if-else chain example. So what's going on here is we have our password. We're declaring our little box here with a password. Then we are reading something into the password from the standard input stream, which is right here. We're reading a number in. So whatever number we put in here goes into our box. And then we're checking if our number is equivalent to this first. We evaluate this first as our first condition. If this fails, then we try evaluating this condition right here. If that fails, then we try evaluating this condition right here. If this fails, we evaluate this condition. And then finally, if all of this has failed, then we execute the code that's just in the else block. If we get rid of the else block entirely, then there's no code that executes, and it doesn't even print out that you failed. So let's see, we can try putting in some of these various passwords and checking if this works. So password, let's try 1234. Password 1 has been input. Let's try putting in 3333. And we put in password 2. Great. 4444. Great, we put in password 3. Okay, so the next thing is you might actually have situations, though, where you want to actually nest if statements inside of each other. So this is a very common thing. So let's actually scan 2 things now. So we'll actually have them put in a username as well, and we'll have their username just be a number as well. So user number, user ID, how about? There we go. So user ID and your password. We'll scan, the first thing that's scanned is going to be the ID. So we'll scan user ID, and then we'll scan for password. So this is where we start getting into either stacked if statements, so nested if statements, or you can also do a combined conditional. So with and. So let's first show off what a nested if statement looks like. So for the person to be able to log in, they have to enter the correct user ID and they have to enter the correct password here. So the first thing we're going to check is if the user ID is correct. So let's have the user ID be if user ID equals, I don't know, what's a good user ID? Let's have it be 1234, sure. And then we also want to ensure that the password is correct. So now we put another if statement inside of this. So the code being executed in here is only being run if the user ID is correct. So here we say, all right, if the password now is equivalent to, we'll have the password be 3333. And here we will print out that they were successfully logged in. Printf, printf, there we go. Successfully logged in. CSS. I don't think that's how you spell successfully, but that is fine. Logged in. Remember, guys, as long as you consistently spell things wrong, it does not matter. For variable names, anyway. Famous piece of advice from my high school programming teacher. Okay, so effectively, now if we put in the correct user ID and the correct password, then we are going to be logged in. So user ID is 1234, and now let's put in the password, which is 333. And we can see that only when we put in both of these, we get that we have successfully been logged in. Now we can add some else statements as well to tell the user what they actually got wrong. So if we've entered this, this means that you got the user ID correct. It was a valid user ID, but you didn't get the right password. So in this case, you would print out something like, you did not get the correct password. So password failed. Password failed. Whereas something over here, if you fail the first test for user ID, you would print out something like username failed, because here they're failing their username check, right? So here we have that we've successfully logged in, but let's say you get the username wrong. So 1235, you say is your user ID. Now we see that we can say username failed. Probably should say like user ID wrong and password wrong rather than failed. Yes, if you misspell the variable wrong consistently every single time, it all works out half-assed. So in this case, we can see that we got the user ID wrong. So it's checking the user ID before it checks the password. So the fact that this fails means that now it's jumping down and executing this block of code. But in this inner block right here, it's basically saying, okay, if we've entered this block already, now we're going to evaluate this condition. And if this fails, then we're going to say the password's wrong. So let's get the correct username, 1234, and let's get the password wrong. And now it's going to say that, yes, so password was entered incorrectly. So there's actually two ways. There's another way of doing this that you wouldn't be able to do the whole password wrong, username wrong thing with, but it's tinier and a lot of people would like that. So instead of having two separate nested if statements here, what you could do instead is check both of them with a logical connector right here with the AND connector. So here we're checking the user ID and the password all in one statement. Give me back my successfully logged in. And if they're both right, then we're able to just print out that the user has successfully logged in. This is a lot smaller. Most of the time, you're going to see people using a ton of logical connectives in if statement conditions. This is very, very common to see. All right. So the next thing that we're going to be taking a look at is probably, I think we should look at switch statements, since they're a more fancy way of doing if-else chains. So can I bring back my big if-else chain that I did? Yep, all right. So this is an example of an if-else chain, and this is horrendously ugly. People hate if-else chains. They're very inefficient, especially so let's go take a look at some of the actual code that's generated for an if-else chain. Yeah, okay, this was after this is after I messed up the passwords here. Let's see. Password. I don't know if the C compiler is actually going to optimize this, but I'll show you what you can do here instead. So there is an equivalent for this. Let me pull up my add new compiler. So we're just briefly going to take a quick look into the assembly to see what's going on behind the scenes here. And effectively what's going on is, I'll move that over there. Where'd it go? Where'd my assembler go? Give me back my assembler. What? I'm so confused. Come on. Give it to me on the bar. What? I'm very, very confused. Wait. Okay, whatever. So as you can see here in the internal assembly that we have here, each of these if-else chains evaluate to some comparison operation. So the if statement up here evaluates to these three instructions right here. And then every time it's evaluating a conditional, it has to execute these three instructions, which is, to put it lightly, rather inefficient when you have large amounts of if statements, especially if this isn't a big for loop that you need to execute millions of times a second, a big while loop, like a game loop or something. If-else chains can be somewhat slow. It's faster to use switch statements because they can be implemented as a lookup table by compiler optimizations. So let's take a look at what a switch statement looks like. So you can't always use switch statements in place of if-else chains. You can only use switch statements when you're doing something like this, where you want to check if one variable is the same as multiple different things. So let's write something that's equivalent to what we have right here. I'll comment this out, and we will show that they are effectively identical. So the switch case statements begin with the switch keyword, switch, and now you have a block here And inside of this block, you put the variable that you want to evaluate against different cases. So in this case, we want to evaluate password, the value of password, against all of our different cases. So for our first case, we're going to be doing 1, 2, 3, 4. So case 1, 2, 3, 4. And second case, we're going to be doing, I should add breaks in here. Break 1, 2, 3, 4. Second case is 3, 3, 3, 3. Third case is 4, 4, 4, 4. Final case is 5, 5, 5, 5. And our default case, DEFAULUT, is what happens for our else statement. So effectively what's going on here is that when you have a switch case statement, you're evaluating whatever this value is against all of the constants in your cases right here. So in this case, password is going to be evaluated as either 1, 2, 3, 4. It's going to be compared against 1, 2, 3, 4, 3, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5. Except what makes this better is that this doesn't have to be evaluated each time. You can implement this in O of 1 time as a lookup table, which is much, much faster. So effectively, each of these whatever this is, can act as an array index into some big static table that has been designed by the compiler. So let's finish this up and I can explain further how this actually works, and I can show that these are equivalent. So we'll put the printf you failed at the bottom here, and I'll have to explain what break means as well. So password 4, password 3, password 2, and password 1. So effectively, no, I don't want to save it. Add new execution only. And I want to put this guy over on the side. Okay. So effectively it's saying we failed right now, presumably because the password that we're putting in isn't actually anything. So yeah, we're not putting anything in, and it's saying that we have failed. But if we put in 1, 2, 3, 4, it should tell us that we put in password 1. If we put in 3, 3, 3, it should say that you put in password 2. And what's good about this, I don't know if we're actually going to be able to see it if we add a new compiler in here, but it's not going to actually have to do. So here it's actually doing faster comparisons. It's doing 2 instruction comparisons, but this is not optimized. If we enabled full optimization, let's actually see if we do that. If it's going to compile this entire thing into a big lookup table, I'm pretty sure this has been converted into a lookup table now. Yeah, this looks like we've converted to a lookup table. But long story short, you're able to get better performance in the event that you have an if-else chain that looks something like this, where you're comparing against multiple constants for a single variable. Way faster to do a switch statement, especially for high-performance applications. So one thing that's interesting about case switches, unlike if-else chains, where you have an if-else chain, effectively what's going on is it's looking and then evaluating one of these blocks. But with a case statement, a switch case statement, you explicitly have to tell it that it needs to break out of this switch statement. So the break statement basically says, jump from wherever we say break to this curly brace right here. So it skips all of the other cases and breaks. But if you don't explicitly say that, you can have multiple cases for the same thing. So one of the main uses here is, say you have 2 password 1s. Say we have wanted 1, 2, 3, 4, 5 to also be a valid password 1. Now it's going to check for both 1, 2, 3, 4, 5 and 1, 2, 3, 4, and then either of these will evaluate to executing this code right here, followed by this break then jumping out of all of it. But you can put multiple cases in here. Say I want 3331 to also be an instance of password 2. So now if I put in 3331, we see it jumps into tier 2 password 2. You can also have other code in here, and so I can put something up here that says you put in the second variant of password 2. So in here it says that you print, let me put a new line there so this can actually be more visible. But here it says you put in the second variant of password 2, then it executes, you put in password 2. But if we just put in 333, it won't execute the top part here, but it's still going through into this other cases block. So this can be, switch case statements can be very useful in the event that you have this specific situation where you're comparing one thing against multiple different values. And it's much faster, and you get the benefit of being able to have multiple cases execute the same code. Whereas in an if-else statement, if-else chain, it makes it, you have to do basically a bunch of ands if you want multiple cases to evaluate to the same thing. So in here, if I wanted to have like the whole special variant thing, I would have to split it up in a completely different way, and it would be more annoying. So we won't go into that since it is 8:39 and I want to try moving along to for loops. But if you have any questions about switch statements, the famous programmer Terry Davis, the creator of Temple OS, once said that the switch statement is the most powerful feature in the C language because it makes things much, much faster than annoying if-else chains. Okay, so next thing we're going to talk about is loops. So the first type of loop that we want to talk about is the while loop. So effectively, when you're doing programming, most of the time you want to loop and execute statements a bunch of times, especially the same statement. You might want the same statement to be executed a bunch of times. You might want it to be executed a bunch of times with a different value. For example, if you're searching something, that's actually on the homework, is we're going to be searching through a list of values and finding it in two different ways. We're going to be doing a binary search and a linear search. But for the first loop example, though, let's just talk very briefly about while loops. So I'm going to do a while loop right here. Effectively, the syntax of a while loop is the keyword while, then parentheses and brackets. So obviously they're yelling at me here. Effectively, you have to put a condition in here. And while this condition is true, this loop will continue executing whatever statements are inside of here. So I'm going to put printf here and have this print out hello for me. And I'm going to put in true here and have this execute forever. This is called an infinite loop because, as you can see, your program will run forever. In fact, in my case, I'm printing out hello infinitely here. But Compiler Explorer gets mad and doesn't let you execute infinite programs, so it actually automatically stops you after a while because it realizes that you have an infinite loop. So they say truncated and they stop you before you can crash their servers. But in our case, we're saying, okay, while true, print hello. So as far as this program is concerned, it is infinitely going to print out hello over and over and over again. And you can see here that it is really trying. This is, look at the scroll bar on the side here. We print out quite a few hellos before Compiler Explorer servers get mad at us and say, no, you're not doing that. So this is very useful for a lot of reasons, rather than just printing out hellos. Almost every algorithm you do is going to be looping over something, somehow. So let's actually take a look at a condition that we change in the loop to have it stop. So one of the most common things to do with a loop is to have a counter. So we're going to have a counter that determines when we end the loop. So I'm going to call this guy counter, and we're going to set him to 0. And we're going to have it be so that when the counter is equivalent to 10, we are going to stop the loop. So here we're going to print, I don't need a semicolon in there. So when counter is equivalent to 10, we stop the loop. So obviously this is, actually I did this wrong. While counter is not equivalent to 10. So this statement is true until counter is going to be equal to 10. I should probably even say counter is greater than or equal to 10 just for safety. That is, you could do either or, but it would be better practice to do a greater than relation here. So while the counter is greater than 10, so actually less than 10, right? So effectively, the counter is going to start off at 0. And then while the counter is less than 10, the statement remains true until the counter becomes greater than 10, or yeah, greater than 10, because we have less than or equal to. This statement is going to run. So to actually get the counter to go up, we are going to put that the counter equals counter +1 in here. And now you can see that we're only actually printing out hello 10 times because we've limited it with this counter. So the second that the counter becomes greater than 10, which is on this line after we've executed 10 times, the counter has done counter +1 10 times effectively, and then the loop is over and you can put whatever you want outside of the loop here. So loop done, loop done. And huzzah, we print out hello 10 times and the loop finishes. And the second this becomes false, it jumps to whatever is right after the loop, right? So this is basic looping right here. So while loops are useful for when you don't know exactly how many times you want your loop to go. So you might use a while loop if you're scanning for user input, and you're unsure if there's some big condition that you're trying to determine whether or not to end a program. What a lot of GUI applications have is a central loop, which they test if the X button has been clicked. And if you've clicked on the X button for the application, then it ends the loop and then closes the program. And probably does some cleanup stuff afterwards as well, which is fancy. But for our purposes, this is a decent example. So next, I want to talk about for loops, because for loops are probably the most useful thing in the C language. I think you're going to use for loops more than any other construct. I'm going to say it's probably the keyword that I use the most. So I'm actually going to write something that's identical to this loop right here. So this combined loop right here can actually be simplified greatly in a for loop. So the way for loops work is they have three parts. There's an initialization stage, there is a condition, and then there is an increment stage. So the common for loop you're going to see is something that looks like this. For int I equals to, I forgot to type the I. For int I equals 0, while I is less than some number, and we'll say 10 in this case, then we say I ++. And then in here, we have code that's supposed to execute, and in this case, we're going to have our hello right here. And this is actually identical to our while loop right here. Effectively, what this is saying, and as you can see right here, it is effectively identical. All that we're doing is we are printfing hello 10 times. What this actually, this literally evaluates, there is a direct conversion between for loops and while loops. Effectively, it's just a more slimmed down version of a while loop. So our counter in this case is going to be I, and we're initializing our counter to some value. So I equals 0. Then we have a conditional statement. So the loop will loop until this condition is met. This actually should be less than or equal to. So while I is less than or equal to 10, then we do I++. This final statement right here at the end evaluates after everything in this body has been executed. So this is every time it loops. This is completely identical to what we have up here, where we set the variable first, then we evaluate some condition to determine whether or not the loop should go. And then finally, we have some statement that we're executing, and then we increment our counter by something. This does the exact same thing. We declare our I to be 0, which is our counter. We are evaluating this condition every time the loop loops through, and we add 1 at the end after our printf. So if I had to convert this for loop to a while loop, I would do int I, and I'll comment this out to show that this is identical, even though it's identical to this one up here, but I'll use the actual I that we have. So it is literally int I equals 0. Then we would have a while I is less than or equal to 10. And then we're executing whatever our loop body is right here for f. And then we do I++ here as a separate statement. So essentially, I don't know why loop done is being printed. Okay, there we go. So effectively, this for loop and this while loop are exactly equivalent. It's just a separate way of writing this because this is probably the most common construct in the entire C language is loops that look like this, where you have some counter and you're determining whether or not to end your looping based on something that is being counted. So there's multiple ways to represent things being counted, and you can do for loops with multiple variable declarations, but that's kind of beyond the scope of this workshop. In fact, I don't even think most people who know C know how to do multiple variables in their for loop. You sometimes will see people with nested for loops, but that is beyond what we are going to do right now. Okay, so the next thing that we're going to briefly discuss beyond loops is, let's see, what else did I want to talk about? So we did for loops, we did while loops. We can do while loops. Do while loops are kind of silly. It's just while loops, except you evaluate the condition at the end of each execution cycle rather than the start of each execution cycle. So a do while loop looks like this. It begins with the keyword do, then there is a block right here, started by the opening bracket and the closing, ended by the closing bracket, and then while, and then you put your condition in here. So this is an infinite. Let me do an infinite loop right here just to demo this really quick. So here we have our infinite do loop. So this prints out hello forever, same as the other one, except now we're evaluating this condition right here at the end after it's been printed. So actually, if I do while and then false, F-A-L-S-E, you're going to actually see that this still prints out hello once. And the reason it prints out hello once is because we always enter the body of the loop the first time. And then if this evaluates to true, then we jump back. But because it's going from top to bottom, it sees the do, enters the loop body, then evaluates the condition after it's been executed. So you do while loops if you always want it to execute the body at least once, and you do while loops when you don't want it to enter the body once, effectively. There's very few cases where you're unironically going to want to use a do while. You almost always use just a pure while loop rather than a do while. So that's our looping construct. The only other way to do looping in C is with recursion, function recursion, which is what we are going to get to next. All right, so let's take a look very briefly again, just back at the syllabus, make sure I'm not missing anything here on our syllabus. Blah, 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 wrong day. If else change, switch statements, ternary operator. Oh, ternary operator is a lot of fun. Ternary operators are just one-line if statement. So effectively, we can do stuff like this. Let's do int I equals 0. Actually, I don't even need an I here. I'll just do an example with printf. So printf, I will have an int I. Int I equals, I'll put the ternary operator there. I'll print out our result here, %d, comma, let's see, I'll print out our I. Okay, so the ternary operator, this is in a few languages. I believe Java has it, C++ definitely has it. Python doesn't have it, which is sad. JavaScript, I believe JavaScript has it. So effectively, the ternary operator takes the form of condition. So there's some condition, then a question mark, and then result 1 and result 2. So effectively, what's going to happen is if whatever this thing before the question mark is, if the condition evaluates to true, or in our case, anything that's not 0, then this is entire expression right here. And let me put it in parentheses. This entire expression evaluates to res 1 if cond is true, and it evaluates to res 2 if cond is false. So this is a very easy way to shorthand something that looks like this. Int I, and then you say if cond I equals res 1, else I equals res 2. So this is just shorthand for this. And typing this out is very annoying. So it's really nice to be able to have something like this where you can do all of this evaluation just on one line. So let's actually show that this works. So they're yelling at us that con isn't real, but if I have cons equals, I'll have con be a bool. Bool con equals true, then we'll have, they're going to yell at me for a redeclaration here, which is fine. I'll just replace this with J. Sure. But we'll have con be true, then we'll have res1 equal 3, and we'll have int res2 equal 5. Okay, so effectively we can see that because cond is true, this expression right here evaluates to res1, which is 3, and then we are just printing out I right here down there. So effectively then if cond is false, this should evaluate to 5, because it's going to evaluate to the second expression. You're free to put in your own things right here, 1 and 0, whatever you want. You can put a constant here, even though I don't know why you would do that. The same thing as if. So because this is true, we evaluate to the first thing, and I become 0. Easy peasy. One reason you might want to do this, especially, is if you have a const right here, and you want to conditionally assign a const value on initialization. It can be useful for doing this as well. There's no way they'll ever ask you about the actual applications of the ternary operator. You should just know what it does for the LinkedIn skill assessment. Okay, so next up, we're very briefly going to talk about functions. So I wanted to wrap things up at 9. We might actually be going till like 9:10 since I'm kind of, crap, did I not go over arrays? I should go over arrays too. All right, maybe we'll go to like 9:15. I'll go over the array data type really fast. So arrays should be like an entire school unit unto itself. So this is going to go somewhat fast, but if you're familiar with a language like Java, this will probably be a piece of cake for you. So we're going to talk about fixed size arrays rather than dynamically allocated arrays. So in C, we can allocate boxes for things, right? So int I equals 0. We are creating a box of 32 bits and putting the number 0 into that box when we have this declaration right here. But sometimes we want to create a list of boxes that are all referred to by the same name. So the way that we can create a list of boxes is by a declaration like this. So int list of boxes. And then effectively what we do is we put a bracket, opening brackets and closing brackets, and then the number of boxes that we want. So int list of boxes 5 is going to be a list of 5 32-bit boxes, all referred to by this one name, list of boxes. It's actually referring to the first box, as we will see later. It's a memory address to the first box, but that will be tomorrow when we learn about pointers. So now the way that we actually put the list into these boxes is we have our, actually think I can do it with these braces. So I'm going to put 1, 2, 3, 4, and 5 into this list of boxes right here. So effectively, what we have here is a list of 5 ints, all referred to by list of boxes. So now, if we actually want to access each of these, so let's say I want to know what's inside of the first box here. The way that we access this is with the array subscript operator. So let's say I want I to be the first box. We're going to say list of boxes and then subscript. This is, so brackets. When you read this out loud, when you read brackets out loud with something in them, you say sub. So this is list of boxes sub 1 is how this is pronounced. And the idea is that it's like subscript, right? So if you have in math, if you have a list of something and you want to know what index of the list something is, you say sub. So you use a subscript to denote that element of the list. It's the same thing in programming, except the first index is always 0. So if I want what's in the first box, it's actually going to be 0 here. So if I actually print this out now, if I print f what's in this first box, so let's print out %d, %d, and then we're printing out I right here. Effectively, we can see that we're printing out 1. So the reason we're printing out 1 is because here we're declaring this list right here of ints, right? So list of boxes 5 values, right? So what this is actually saying is that we are creating 5 integers, and here we are initializing them with an initializer list. So we're putting 1 into the first box, 2 into the second box, 3 into the third box, 4 into the fifth box, into the fourth box, and 5 into the fifth box. But now when we actually want to get what's inside of the box, we say list of boxes 0 equals, so we're retrieving what's in the first box with list of boxes sub 0. So you can use these effectively as variable names. So you can do assignment to this as well. So I can get I here, but we can also treat list of boxes as an L value from yesterday. You might remember L values yesterday used to be only variable names, but now we can also have arrays with a subscript be L values as well. So this is actually assignable. So I can set the first value of this list to be something completely different. I can put 40 into there, and then I can do this entire thing over again and print out what our new value is. So I can say that I is now going to be equal to the new list of boxes. And now we should see that I should probably put a new line here so this you can actually read this. So here you can see that first things first, we have our list of boxes right here. We put 1 into the first box, 2 into the second box, etc. Then we're reading what's in the first box right here into a new variable called I. Then we print it out 1. Then we reassign what's in that first box to 40. Then we reset I to what's in the first value of the first box, or the first box. Then we print it out. So huzzah, this is arrays in essence. It's nothing, for those of you who have already seen arrays, nothing too out of the ordinary, I assume. It's very similar to Java arrays, except for the fact that you don't use the new. You literally are declaring a fixed size array using the type, the name, and then brackets and the size of the array. So this is a list of 5 things. So one thing that you might want to do is to actually operate on this list. So the way that you would operate on the list with a for loop is the most common way of doing this. So you have for in I equals 0, while I is less than the array length. Okay, so in Java, you have an array length operator. So you use something like list of boxes dot length. That doesn't exist in C. There's no such thing as the length operator. You quite literally have to save the size of the array completely independently. So most of the time when you see someone passing an array to something, they pass the size with it. But actually, because list of boxes is a fixed length array, I can probably do the size. I doubt size of operator is going to work on this. I'm assuming no, they're not going to like this. So if I do I++. If this works, this will be a miracle. I'm pretty sure you can't do size of on here. Feel free to talk to me about this in DMs if you have no idea what size of is doing. List of boxes, I'm just going to printf it. Printf %d and list of boxes. And then we're going to do sub I, and this is going to be retrieving the ith element of list of boxes here. So let's see. So this should print out our, yeah, I didn't think that they would like that. So we're going to just do through 5. Okay. So effectively, we can see that this prints out what's actually inside of here. I'm going to put a new line here. And what this is doing now is printing out what's in each of these boxes. So we have an array of 5 values with 1, 2, 3, 4, 5. And this for loop right here loops through every element of the array and simply prints out what is in that position. We are changing the I every iteration of the loop. I starts off as 0. Then on this first loop, we print out what the 0th box is. The second loop, we print out what the first box is, etc. until we hit 5, which is the length. And remember, the indexes start at 0 and then go up to the length minus 1. So while we're less than the actual length, that's why we do I is less than 5 and not less than or equal to 5. If we tried equal to 5, this would actually be an out of bounds exception. But keep in mind that we're not actually checking out of boundsness in C. There's no, unlike Java, where this would throw an error that you've done array index out of bounds. C is meant to be very fast and low level, so it will literally, C will happily go into, I can print out hundreds of values here, and now we're just printing out random jargon in memory because it does not actually care that that it can stop at it actually doesn't care that this array is only 5 things long. It will keep trying to get things in memory past that. So as you can see, it goes well out, and you can say, okay, we're going to keep grabbing new values from this array, even though the array is clearly only 5 things long. So it's always important to remember and see, don't exceed the length of your array. It's not a good idea. Okay, so you can also do bounds checking yourself, but that slows things down, obviously. So let's see, that was arrays really quickly, and the only other thing we're going to be covering tonight is functions, which are how you divide your C program up into little itty-bitty manageable pieces. So first things first with functions, you've already seen a function. We have a great function right here, int main. So a function is effectively a black box. So you put stuff in, you get stuff out. So a great example of a function, if I can pull up my MS Paint, pull up Paint. You might be familiar with functions from high school algebra, where you would have f of x equals x squared. So effectively, we have a similar thing that's going on in the C programming language, where you're able to declare some operation to occur with some name right here, and some input that is evaluated for your given operation. So effectively, you can view this as a black box that takes in some input. So something is going in. The thing that's going in is our x. And then we're doing some magic in here and computing some new value, n, which is going to be equal to x squared. And then we are outputting our n value right here. This is all functions do, except functions can get very complicated. We're not just squaring numbers anymore. We're doing big fancy things where we're running entire huge computations in these functions and executing arbitrary code in functions. So let's take a look at our nice x squared function. So the first part of a function declaration is the return type. So the return type is actually the type of whatever variable is coming out of this. So what's actually coming out of our square function is an int. So we're only going to be doing integer squares. So int, and then the function name, we're going to call our function square because we're squaring something, square. And then we're going to write what our inputs are to the function. So the way that you write your inputs are the type. So we have an int, and we're going to be taking in an integer named x. And then we have a block here, and this block represents code that's going to be executed and is eventually going to return something for us. So int square with int x being passed in, what we actually want to return from this function is the result of this. So there is a keyword in the C programming language, which you probably saw yesterday, called return. And what this does is actually spit out whatever this computation returns. So we are going to put in x times x. So that's x squared, effectively. And this is our little function here that squares the number x. So now this will evaluate to x times x when we call this. So I am going to now printf %d, and we are going to have an int here, and we are going to assign our int result to our function. And to our function, this is called a function call, we are passing in what we want squared. So I'm going to say, let's square the number 5. And now result is going to be assigned whatever is returned from this function. So we pass in the number 5. 5 is going to be going in here. Then this is going to be computing 5 times 5. And then this square 5 is going to evaluate to whatever is returned by this. So the result is presumably 25 being stored in result. And now we are going to print this out. And we should see, yes, we returned 25. Huzzah. So this is a very, very basic function. obviously we can compute very big, complex things in here if we want, beyond just squaring things. We can have loops in here that run very fancy calculations. So say another example, which is probably a bit more complicated, is let's sum a list of numbers. So if I sum, so we'll have a thing that sums a list of 5 integers. So int list and of size 5. So we're passing in a list of 5 numbers into this function, and we want to add all of them up. So we'll have an integer here that represents a running sum of these numbers. I'll call it s. We'll set it equal to 0. Then we're going to loop through the entire list. I equals 0, while I is less than, the length of the list is guaranteed to be 5 in our case. So while I is less than 5, I plus plus. Then we literally just say that s is equal to the current value of s plus whatever our list sub I is. And this would sum up everything in a list of 5 numbers, and then we return the total sum. You could also have this be an average if you just wanted to divide by the number of elements by simply doing a division by 5 right there. So let us now print out the sum. So our result is going to be sum, and we are going to be passing in our, I'm actually going to need a list to pass in. So let's grab this and list 5, and we're going to have it be 1, 2, 2, 3, 4, 5. That is 6 numbers, not 5 numbers. There you go. And then we are going to run sum on the list that we pass into this function. And they're mad at me because I forgot a semicolon somewhere, and it is right there. And yes, so now you see 1 plus 2, 3, 5, 3 plus 4, 7, 12 total. So effectively what's going on here is that we are running some computation on some input and then returning this type right here. So you can also return more complicated types. You can return pointers to things, but we will discuss that more tomorrow. We're not going to talk about pass by value versus pass by reference until we talk about pointers tomorrow, since it doesn't really make sense passing anything by reference right now. Anyway, effectively, functions function as black boxes that take something in and put something out. So there's multiple reasons that you would use functions in your program. The main reason I can think of using functions is code clarity. It's not good to have all of your code in one big block. It's much better to separate it up into logical units that make sense, that are easily testable. So that's one of the main things that you would use functions for. Sometimes functions are also, this application of functions that I just described is sometimes called procedures, because procedures run big blocks of code that effectively are easy to debug. There's another reason that you would use functions, and that is code reusability. Every time you want to sum something, it's much better to have a sum function that you can call very easily, rather than writing the algorithm to sum something up every single time in your main function. It's much better to have something, so this is completely reusable. I can change my list very easily. So if I now change my list and I say that the first element of my list, so list 0 is now 100, and now I want to resum this, I can now change the result and say that the result equals something entirely different. And let's take a look. Result is now going to be, yeah, so the sum of this is now, I actually need to do a new line here so we can actually see that difference. So the first list sums to 12, but then after I change the first element from a 1 to a 100, now we see that the sum is 111 instead. So effectively, we're able to call the same piece of code multiple times with a different input and get different results out. And this is what makes functions so powerful. This is the functional programming paradigm. And this is incredible for us as programmers because it lets us reuse stuff that we've already written and write for more general cases, which actually saves us a lot of time in the long run, because otherwise, God knows, we would literally be doing something like this every single time. So we would have the result equals 0, and then we would have this piece of code right here, and then instead of saying this, we would say result equals s, and then we would do this all over again down here, And yes, this works, but it's not nice because it's big and chunky, and I'm not declaring S here, but you get the general idea. So yes, this gives us the same result, but look, we've rewritten this entire algorithm twice. This is unnecessary. Much better to write it once up here and then functionally recall code that we've already written with a different input. So that's functions. I can talk briefly about recursion. So everything that you can do in a loop, you can do with function recursion. Recursion deserves like an entire week in a comp sci class. But we'll very briefly talk about recursion in the context of a factorial function. So there's two different ways of writing the factorial function. So the first way that a normal person would write a factorial function, so we're going to call this fact for the factorial. So what's the input to a factorial, right? Do you guys remember how factorial works? So it's going to be some number exclamation point. And what this means is you're multiplying n times n minus 1 times n minus 2 all the way until n is equivalent to 0, right? So, or not 0, until n is equivalent to 1. If it was 0, the entire result would be 0, right? So until you get all the way down and the expression is 1, right? So factorial of 5 is 5 times 4 times 3 times 2 times 1. So there's multiple ways to write this program, obviously. So the first thing that we would think of is probably, so I'll pass in the n here, is going to be a loop-based solution where you have some number and you multiply that number until you reach 0. So you would have for I equals in I equals 0, while I is less than our n, or you know what, no, I'll have it be so. I is greater than or equal to 1, and then each time we're going to subtract from our n, but no, you know what? I can just use... I'm debating whether or not I want to go up to the n or go down. It doesn't matter. I'm going to go up to the n because that actually is a much nicer algorithm. So while I is less than or equal to n, and you start with I equals 1, then you do I plus plus, and we're going to multiply our numbers. We're going to have a running total, which we can actually start as equal to 1 in result equals 1. And then we are going to say, all right, so until we get up to n, we are going to multiply our result times equals. So remember that times equals just expands to equals result times something. So result equals result times our I here, and this should compute the facts, and we have to remember to return our result. And put the semicolon there. And for the sake of not having to type out printf, I'm just going to return this as the program output. Return, that's not how you spell return. That is also not how you spell return. Return fact of 5. So this should be 5 times 4 times 3 times 2 times 1. And we see that that is 120. I know for a fact off the top of my head that's the correct answer. Feel free to verify the fact that that's the correct factorial. So effectively what our algorithm here is actually doing is it is saying that, all right, we have our 1 as our initial value. Then we're going to multiply 1 by 1. Then we're going to multiply whatever this is by 2. And then we're going to keep going up until this condition halts, which is while I is less than n, less than or equal to n. So while this is true, we're going to keep doing this. But eventually, we're going to get up to whatever the n was that we put in. That's going to evaluate to false, and then it is going to stop running this computation. So that's one way of doing it. Some people prefer to compute it down instead of up, so they're computing from the top down. Technically, we don't need all of these fancy variables in here. We really only need one. We could do away with the loop counter entirely. We could also optimize this, so we start at 2 instead of 1, because technically we're doing a 1 times 1 here, which we know for a fact is just 1, so we can eliminate this by starting at 2 instead. That's a very small, minimal optimization that really wouldn't be very useful. We can make this smaller by saying times equals 1, or times equals I. And then we can get rid of brackets because you're allowed to get rid of brackets if you only have one statement. And huzzah, this is how I would probably implement a basic factorial function. So this is one way of implementing the factorial function, but we can take a look at a recursive solution instead, where you have a function call itself. So one thing that's interesting about the factorial solution is that factorial of n is actually equivalent to saying n times n minus 1 factorial. So as you can see, there's actually a factorial call inside of this factorial, but we're multiplying n by the result of another factorial on n minus 1. So a better way to implement factorial in a language like C, hang on, I've apparently lost my Google Chrome instance. Here we go. So I'm going to do int fact2 over here. Int fact2 pass in n is to literally call the factorial function on itself for one less than what we currently have. So here we do return n times fact2 of n minus 1. And now we're passing n minus 1 in as the new thing that we're evaluating for. And this, we have to have a base case as well. So I can't just have it do that. Let me actually check. So if n is equivalent to 1, then we're going to return our 1, right? Because that's the base case. Once we get down to 1, then we just want it to evaluate to 1 and then keep multiplying up the chain. So return 1. Otherwise, if we're not doing that, then we're returning. I should probably add an else here just so you can read this better. But effectively, base case and then recursive case here. So until n is equivalent to 1, we are going to multiply by ourself effectively n minus 1. And eventually, we're guaranteed to get down to 1 here. And then it will return 1. Then that will multiply by n, and it will just return up this entire chain. And we will see that it evaluates the same thing. So if I actually do this right here, if I compute fact2, we see that the program also returns 120, which exact same thing right here. So a fun programming fact that is probably one of the most important programming facts is the fact that any loop-based solution, anytime you're using a loop, you can always implement that using a recursive solution instead. There's always some way to implement loops recursively. So in spirit of that, I am going to put onto the homework as a bonus section for question 2, bonus, that if you want, you can implement the search algorithms recursively rather than with a loop. So the normal way you implement a search algorithm for an array is just a for loop and then an if statement and some combination of logic. Same with binary search. It's also just a binary search is a while loop. But long story short, you can implement all of these recursively instead of with a loop. So it's called the iterative solution versus the recursive solution. So implement as both iterative solution and recursive solution. All right, so I think they do not like this. Did I spell something wrong? No? Okay. Well, so does anyone have any questions about anything we covered today? I went like 20 minutes over. My apologies. I'm glad I didn't go an hour over, but I underestimated the fact that I had to cover. I think loops was what tripped me up. I spent too long going over loops. Anyway, if no one has any questions, we can wrap things up, but I will stick around afterwards for questions. And so I guess I can talk very briefly about what the homework tonight is. The homework tonight is going to be constructing a function that takes an input float x and an integer exponent n and computes and returns float for x to the n. I showed you how to square than x, but now you're doing x to the power of some n. So now you're giving two things, and I guess I can actually show a function that takes two things. I'll write a really quick function that takes two things. I'll write an add function that adds two numbers, int a and int b, and we are going to return a plus b. This is a very basic function, takes two inputs and spits out one input, which is going to be the two numbers added together. So this would be add, and then this is two inputs, add 5 and 5. So this just computes 5 plus 5 inside of this function, and then returns the result, and obviously the result is 10. Easy peasy. This is a function with 2 inputs. So what I'm asking for tonight is an exponent function, exponent, which takes in an integer x. No, it takes in a float. So I actually want this to return a float. So this is going to be a float exponent, which is going to take a float x and is going to take in an integer n. You're only going to be doing integer exponents, not floating point exponents. Otherwise, you would have to use the special formula. I'm just expecting a loop here, essentially, that computes the result here. So that's the first question. The second question is I can go over void functions. All right, void functions, easy peasy. Void functions are just functions that don't actually return anything. So void, normally use void functions for stuff like printing things out. So something like a print list function, where effectively you don't want print list to actually return anything. You just want to run your prints in here. So printf %d, something like this, where for and I equals 0 while I is less than, and I'll pass in a list of 5 things, sure. And so this will be something that prints out a list of 5 things, I++, and we're going to be printing out the 5th element of this list stuff I. And effectively, all we're saying here is this doesn't actually need to return anything, because all it's doing is acting as a reusable list printer for us. So print list, anytime we have a list of 5 things here, whether that be, so we'll call this int list 5, and we'll have this guy be, so this will be list 1, and then we can have, why don't we do 2 lists? So we'll have this be list 1, we'll have there be a list 2 down here. All right, we'll call this guy print list 2, and we'll print list 1, and we'll print list 2. So effectively, I'm really just demonstrating that functions are meant for reuse here. So I'm gonna get rid of this add. I'm gonna have a return statement. Long story short, void functions, no return, does not return anything. So list 1 is going to be, let's say 1, 2, 3, 4, or I clearly missed a number in there. That is fine. And let's do the second one and have it be 4, 4, 4, 4, and we're getting rid of this guy right here because he's irrelevant. And as we can see here, all that's happening here is that the print list function is being called twice for 2 different lists, but we're able to get the code reuse here. And we actually don't care about what print list is returning. It's not returning anything. It's just a chunk of code that takes some input and has no output, but is doing some operation. In our case, printing. This is really the only application we'll be seeing of void functions. Sometimes void functions can do more advanced things that we're not going to get into, modifying global state, which we are definitely not going to be modifying global state as a sin. Never modify global state. Okay. So next up, let's see. So what I want is a void function that takes a character and an int n, and then prints an n by n square made out of whatever character you pass into the console. So remember that you print with %c for characters. So if I give you the character star and the number 5, I want a 5 by 5 square of stars on the console being output. So you're going to scan, I guess you can scan F and ask the user how big of a square they want, but effectively, I would just want you to print out a big square of whatever character has been passed into the function. Okay, so obviously that's going to be a double for loop, nested for loop, if you want to attempt that. If you have no idea what that means, my DMs are open. Feel free to contact me. All right, part 2, which is the big thing for tonight, is going to be search algorithms. So I want you to create a function that takes an array of 5 unsorted integers and a number to find, which is your second parameter, and then return the index of where the number is, or a -1 if the number is not found. And I want you to implement this using linear search. If you don't know what linear search is, Wikipedia it. The next thing is binary search. So this one's going to take 10 sorted integers and a number to find, and then return the number's position or -1 if the number is not found. And so this is going to use, I say for loops here, but this is actually, I believe binary search, the typical implementation of binary search uses a while loop. If you can avoid finding a C implementation of this and finding a pseudocode implementation instead, that's probably better. But if you can also look up what binary search does, and then you can reason through how it works and implement it in C from scratch. That's even better because that's going to boost your algorithmic reasoning skills. And then obviously I've given this bonus here. Any recursive solution, any iterative solution can be implemented as a recursive solution. So implement the recursive solution and iterative solution to both of these searches if you're feeling very, very ambitious. I think I'll try having both for tomorrow just as a fun little exercise. So these are the most basic algorithms essentially that we're going to be taking a look at. Then finally, while loops in action. This is a fun one. Construct an algorithm that prints out all prime numbers up to infinity. This is going to require a double nested while loop. So effectively, all I'm expecting you to do is come up with a program that has a number, figures out if it's a prime number, then checks the next number, sees if it's a prime number. If it's not a prime number, if it is a prime number, print it out, and print out all prime numbers. Obviously, this isn't going to go really up to infinity since integers are only 32 bits. So I'm happy even if it loops back around and goes into the negatives. It's whatever, it does not matter. Just assume that integers are infinite. And don't even worry about integer size limits. You'll be fine. Okay, so those are the homework questions. Does anyone have any questions about anything we covered today or the homework questions that I have laid out?